On most days, we get a chance to see the International Space Station crew members working on science experiments. Sometimes we get to see the experiments themselves as they do their thing. Recently, the International Space Station Program Science Office posted a video clip on the Real NASA YouTube channel from a combustion experiment that's underway, and that clip has caught an awful lot of attention. Look for yourself and see why. That's from the Flame Extinguishment Experiment 2, or FLEX 2. Earlier this week, I spoke with Dr. Tom Avedisian of Cornell University, who is the FLEX 2 co-investigator who requested that particular test burn, to find out what it is we're seeing here and what scientists are trying to learn from burning things in space.
Well, our overarching objectives are to obtain information about how liquid fuels burn so we can design ultimately more efficient combustion engines used in transportation systems on Earth. The problem with that is that real liquid fuels like gasoline, diesel, and jet fuel are so complex that it's really a hopeless task to develop models for how they burn, as they contain hundreds of miscible constituents with a wide range of boiling points, propensities to form soot during combustion, and heats of vaporization. Soot is the black carbonaceous material we sometimes see spewed out of the exhaust line of diesel trucks, which is responsible for a whole host of health risks. Where we are addressing this problem, our approach, by studying the combustion dynamics of fuel blends comprised of a much smaller number of constituents, say for example 2 or 3 ideally, with the hope that they will replicate certain combustion targets of the real fuel. We would then develop the understanding of that simpler blend, which we call a surrogate, and use the combustion properties of the surrogate to assess the performance of the real fuel.
Now, in fact, you're doing these experiments in space by burning just single droplets of fuel, right? Tell me why you do it that way.
Well, that's correct. Our strategy has been to develop the combustion properties for evaluating a surrogate by using the simplest possible configuration of burning for a liquid fuel, namely a droplet burning under conditions that promote spherically symmetric gas transport. This kind of combustion symmetry is currently the only one for a liquid fuel that can be modeled using detailed simulation or first principles approach, where no submodels or adjustable constants are required. This is precisely what is needed to evaluate the efficacy of a surrogate to perform like a real fuel it is intended to replicate.
And in space, you get to do these experiments inside an apparatus called the multi-use droplet combustion apparatus that allows you to control variables, right?
That is correct. The MDCA, as its shorthand notation, has the capability to control the droplet size, which is a very important parameter that influences soot formation and radiative losses, as well as the ambient oxygen and inert gas concentration and pressure up to about 3 atmospheres. Currently, we do experiments. My component of the FLEX project is essentially at room temperature air. Obviously, the facility includes storage chambers for a range of fuels, with the ones we are investigating being representative of components of real transportation fuels.
Now, we mentioned earlier that there's a video on YouTube that shows kind of a remarkable burn, and I'd like to play that again and have you describe for me what it is that we see in this video.
Okay. This is a very delicate operation. There's a zooming out, and you'll see very quickly the activation and the ignition event. The droplet looks motionless, but actually it is moving a little bit. And you'll see in the lower left-hand corner the flame disappearing and then reappearing. And we believe that this is the result of movement of the droplet, such that when the droplet is moving, fresh oxygen is drawn into the combustion zone, but it also depletes the oxygen on the backside of the droplet, which causes extinction. But that movement of the droplet allows the flame to close on the backside. The continued movement, it opens up again, and you can execute multiple cycles of this, what appears like a jellyfish type of motion. I mean, we don't really know the detailed mechanism for this. This is purely speculation on our part, but this is what we think is happening.
But as you explained earlier, one of the things that you're looking at is what happens to the soot during these burns, and you really can't see that in that video, but you provided us with another video clip from a black and white camera in the MDCA. I want to show that because it also has some pretty remarkable movement in there, and get you to describe what we're seeing.
Well, this video is of a toluene fuel. Toluene is a constituent of gasoline. Here you see, as soon as the ignition process occurs, soot explodes into view. And as you noted, this is a backlit image, so we see the droplet, that's the black ball that's kind of very slowly drifting, and the soot particles are almost in the state of animated levitation around the droplet. The flame is actually extinguished, but you can't see it here. The droplet is drifting, but the soot particles remain somewhat in place. That is a remarkable illustration of the formation of soot under the spherically symmetric condition.
It's remarkable, even for the layman, to look at that and to have just a beginning of an understanding of what we're seeing there. Can you explain to us how you imagine the results, what you're getting in these burns, how they can be applicable in future uses?
Well, as I remarked earlier, we have been using the multi-user droplet combustion apparatus on the space station to study how surrogates for real liquid transportation fuels burn when subjected to the idealized environment of no convection and no relative droplet gas velocity. That's going to create spherical droplet flames. We feel there are few configurations better suited to get this type of understanding. I would also note, or like to note, that with the new generation of fuels emerging that will be derived from a wide range of biofeedstocks like algae, camelina, soybean, and so forth, the MDCA, with the spherically symmetric burning process that it can promote, is, I think, well positioned to reveal the influence of fuel composition and droplet size effects on ignition, combustion kinetic mechanisms, and so forth that control burning. Developing surrogates for these biofuels is essential to access this information, and armed with it, the combustion chemistry for these simpler blends. Other characteristics of biofuels can be obtained that should ultimately allow us to predict their performance in combustion engines for this new generation of fuels.
Be very interesting to keep track of this as it goes forward and see how it works. I appreciate you taking the time to explain it to us. Thank you very much.
My pleasure.
Dr. Tom Avedisian of Cornell University is a co-investigator of the Flex 2 experiment on the International Space Station.